adverts here. First of all, I would like to let everyone that we are know everyone that we will record this session, so we make it available for members of the society and also interested groups. Always following the GDPR. Please, if throughout the presentation, please try to mute yourselves. Unless you want to ask a question, but we'll leave the questions and comments for at the end of the presentation. So everyone is encouraged and welcome to join us as members of the society. So if you want to apply and know more details about our society, you can enter to IHFES.org for more information. And we have a couple of announcements. One is that on the 18th of June, we are hosting the annual conference to celebrate the 30th anniversary of the society at the St. James's Hospital. We still are accepting submissions until the 10th of May. So please feel free to join us and make your submissions. For more information, you can find it in our website. Another event that is related to healthcare systems, ergonomics, and patient safety. This conference is going to be held from the 18th to the 20th of June in Trinity College. So if you want more information about this conference, you can access the website here below. Okay, and now I would like to introduce you to a very special speaker for us, because he's going to be speaking about the extended reality for explainable human-robot collaboration. He is Mark Zolotas, and he is done a master's in engineering and PhD from the Department of Electrical and Electronic Engineering at Imperial College London. Then he joined the Northeastern University as postdoctoral associate, and then he transitioned as to a research scientist in the same university, working in the Institute for Experiential Robotics. And since then, Mark has led multiple funded projects on collaborative robots and extended reality, including NSF and DARPA grants. So without further ado, I want to hand over to Mark. Thank you very much, Mark, for your time, and we are really looking forward to hear your presentation.
Great, thank you, Diego, for the introductions.
So I'll start sharing. Stop sharing my screen. So
perfect. Yeah.
So you can share yours.
Can everyone see my screen fine?
Yes, we can. We can see it.
Perfect. Okay. Yeah. So thank you again, Diego. My name is Mark Zolotas. I'll be presenting a talk on extended reality for explainable human-robot collaboration. But I'm going to mostly focus on telerobotics as a collaborative paradigm. So introductions-wise, I probably don't need to go over much of what Diego's already said, but in brief, most of my education is from Imperial College London. In my PhD in robotics, I mostly focused on assistive robots, mainly this robotic wheelchair platform you see in the bottom left. But since moving to Northeastern University for a postdoc in Boston, I've diversified into other forms of collaborative robotics, such as teleoperating robot arms, more of the sort of military applications of remote control of vehicles, arms, and such. And I'm currently a research scientist in the Institute for Experiential Robotics. But in terms of what I want this talk to be about, first, I'd like to maybe give a bit of brief background for those of you in the audience unfamiliar with extended reality and specifically its applications to robotics. I'd like to show its utility and dive into the research question that I'm focusing on here of explainable robots. So to begin, I'd like to just define what I mean by extended reality. So this is the spectrum that encompasses virtual reality, augmented reality, and mixed reality. And most of you are probably familiar with virtual reality and augmented reality, where virtual reality refers to a fully immersive digital environment. So you can think along the lines of the metaverse. And then augmented reality is when you have overlaid digital content on the real world. So you can think more along the lines of, say, Pokemon Go. But mixed reality is a little more nuanced and actually considered to be one of the most immersive experiences one could create. It's like augmented reality, but the key difference is that the digital content is more integrated into the real world. So you have to think more along the lines of coexistence. So for example, in mixed reality, one could have a virtual object and it is not allowed to pass through a person, let's say, if they come into contact. So instead, in mixed reality, you'd have the virtual object developed to, say, move around the person if they come into contact. So it's a more seamless experience. And there are different types of devices that are capable of supporting extended reality technology. But I'm going to mostly describe work related to headsets or head-mounted displays. So just for audience's reference, a bit of brief history of extended reality headsets in general. They've been studied for decades now. One of the earliest and most notable prototypes is Sensorama from the early 60s, where this box-like simulator gave the spectator the sensation of reality through moving color images and sounds. This was more of like a box type of simulator, but the later Sword of Damocles, I believe conceived by Ivan Sutherland at Harvard in 1968, is typically recognized as the first head-mounted display, and that actually had like head tracking and all of the same features of having projections in 3D space. And beyond this, the early beginnings of these types of headsets, all the way into the sort of 70s and 80s, were driven by military and academic research projects for purposes such as NASA, pilot training. And so there was a lot of interest during these years in these types of headsets, which led to the 90s having a revolution towards commercialization. However, many of the products that were developed in the 90s, such as Sega's VR headset or the Nintendo Virtual Boy, failed to actually launch as products because of various reasons, some of which are due to lack of portability of these devices. They still had plenty of problems with nausea, subpar virtual experience, and there were known to be hazards from prolonged use of these devices. So I'm not going to talk too much about the commercial woes at this time, but despite these challenges, the 90s also saw a very important milestone, which was the introduction of augmented reality headsets, namely through the system you see on the right-hand side, known as virtual fixtures. And you can think of virtual fixtures as being analogous to a physical fixture, something like a ruler, where the aim of using this headset was to give people the ability to do something like draw a straight line without actually having to have a physical ruler in place, and instead using a virtual ruler to guide the operator as they draw a straight line. So due to the commercialization challenges, unfortunately, while we had the AR headset introduced, many of the other types of headset advances were a little quiet. And so in 2000, there was a period of not much progress in this area. That being said, from 2010s onwards, and this is largely due to Oculus Rift, which made a great petition to sort of revive interest in these headsets. Because of things like advances in GPUs, display technology, sensors, motion tracking, there have since been numerous great devices that have come out in the 2010s and 2020s. And of course, the surge in the gaming interest industry and consumer electronics such as smartphones, tablets, they all led to this, this natural, more pervasive introduction of these devices. And I'm sure most of you will probably be familiar with some of the headsets seen here, but note that they are continuing to be released even today. So like the Apple Vision Pro was only released earlier this year. But that's enough about headsets. I want to talk more about now their popularity leading to more applications in areas other than gaming and entertainment, such as robotics. And some examples you can typically find are, say, using virtual reality as a simulator to train workers in facilities, or in the case of augmented reality, to actually interact with robots, like asking this legged robot to follow the person, or also using AR to expose information about a workflow process involving a robot. Which I'm going to focus a lot on that idea of having an augmented reality sort of exposition of robots. And I'm going to refer to it quite often as robot to human transparency. And then, of course, another classical application of extended reality in robotics is robot teleoperation. So before I dive into the main topic of explainable robots, I also want to emphasize that the growth in extended reality has resulted in fantastic tools for easy integration with robotics. So, for example, this video on the right, it shows how using a standard robotics visualization tool on my laptop, I was able to edit this hologram of a robot in real time. And so this natural kind of two-way communication process is quite straightforward to create once you've kind of become accustomed to these open source software tools. So I encourage anyone to explore them, and a couple of review papers I have at the bottom of this slide also give a good overview of your different options when it comes to these tools. Okay, let me now introduce what I find fascinating about extended reality and the challenge and possibility of making robots, quote unquote, explainable, and how I think this is extremely important for the future of human-robot collaboration. And I'm going to use teleoperation as a motivating use case. Reason being, it's a classic application of human-robot collaboration. It's extremely beneficial for many complex real-world settings, specifically where, say, the robot cannot perform the task autonomously because human supervision is required, like robotic surgery or remote patient care. But another key reason why you might want to remotely control a robot is to avoid putting people into situations of risk and danger, such as in bomb disposal or space exploration. Now, the question that arises, though, is teleoperation actually easy? And the answer is not always. In fact, for robots with many degrees of freedom, such as an arm or this humanoid robot that you see in the image, remotely controlling these robots is extremely difficult and can exert excess workload on the operator, especially if they're a novice user. So a common paradigm is to think about introducing shared control or shared autonomy. And this provides human operators the ability to have autonomous assistance by combining the control inputs that would come from a robot autonomy with those that would originate from the actual human operator. And the Vita arbitration function here in this diagram actually describes how this blending process takes place. And in many paradigms, it's a very simple linear weighting of the control inputs that come from both agents, with this theta parameter defining how much of the person and the robot autonomy contribute to the final system's behavior. Now, the question arises, does shared control actually pose any new challenges in this collaborative experience? And this is something that's for me, an interesting area to address. It's that, yes, in fact, most users do struggle to understand the assistance provided by shared control. So for example, in this video on the right, a person is trying to navigate a wheelchair, a robotic wheelchair through a doorway. And here you can see that this is misunderstanding because the underlying autonomy is, say, assisting by trying to prevent them from crashing into the sides of the door. But this can often end up conflicting with how the user expects the robot to behave. And so I typically refer to this as a mental model misalignment. And it can possibly be attributed to the lack of communication or transparency between the human and robot. In which case, we need some kind of human-robot interface in order to bridge the communication, provide user feedback. And I personally believe extended reality headsets are particularly suitable for this need, as they offer this heightened sense of immersion over other types of feedback interfaces like monitors or projectors. And they also have a rich multimodal sensory feedback capability, be it visual, audio, haptics. So this is why I advocate for these particular interfaces. As I push into the direction of discussing how we can make robots explainable, and bear in mind, I'd like to emphasize it's a very early stage of development in my research. I think this is a long direction of research ahead of us as a community. But I want to briefly make a few points about terminology. So many of the key terms in the broader literature on explainable artificial intelligence, such as explainability, interpretability, transparency, these terms are constantly evolving and they are often used interchangeably in different contexts. So I just want to make clear before moving on that I view transparency as a communication bridge of intent between humans and robots, where I think of robot to human transparency as the fact of revealing a robot's intentions or their plans to interacting humans. And then vice versa, the human to robot transparency is concerning a robot's perspective of the latent human states, or in other words, things like their intentions and their plans. So in my view, any robots that are equipped with feedback mechanisms that can actually improve a user's mental model of the robot's behavior, whether it be verbal, visual feedback, it doesn't matter. Any robot equipped with these mechanisms falls under my classification of explainable. So with this, I'm now going to introduce my prior research on making robots explainable, specifically using extended reality headsets, not other types of interfaces like haptic feedback. And I'm going to start with work from my PhD on using augmented reality to explain the shared control assistance that was provided by this robotic wheelchair I developed. So augmented reality is generally useful in settings where people need to act on their physical environment and maintain high situational awareness. It can also be great for training users. So in fact, my research here began by looking at AR as a way of training people to better understand the underlying shared control of the robotic wheelchair, sort of motivated by that earlier video I showed of a doorway navigation. And here what I did was I exposed the shared control by showing visualizations like green obstacles when collisions were detected, or directional arrows to indicate the different control commands coming from the autonomy and from the human driver. So that's the sort of overview of the first system I developed. But I want to mention that one of the main challenges in many of these human-robot collaborations where you're fusing augmented reality headsets onto robots is the alignment of spatial awareness between the AR device and the robot. So in other words, the co-localization problem. Now, in the robotic wheelchair example, a person is going to perceive the environment at a completely different frame of reference to the wheelchair. So in order to actually align these two mismatched coordinate reference frames, I extracted, in this particular application, the sensor data that was coming from the wheelchair, which was basically in the form of laser readings, and then processed it as an image. But the critical step I want to highlight really is step 3. And this is about the alignment. This is where an optimization problem needs to be solved in order to work out what is the optimal rotation to align the 2 different coordinate frames of reference. And by doing this, once this is done, only then are you able to have visualizations like these green circles at collision points, or a gray path for the wheelchair's future motion. Only then are you able to have them displayed in the environment correctly relative to the driver's headset view. So this is a critical consideration. In fact, one of the main contributions of my earliest work in this area. But beyond that, I also want to note another important criteria when looking at, say, extended reality in robotics, and that's the importance of running user studies in order to evaluate the effectiveness of different types of AR or XR cues in general. And in the context of robotic wheelchairs, this could involve having subjects complete routes with and without augmented reality aids. And then from these studies, you can record various objective and subjective metrics, like task completion time is a standard one, number of collisions, survey responses, and then interestingly, information about eye gaze or head dynamics, all of which will inform future iterations of your extended reality interface. And in fact, that's what happened in my case. Following initial work, I developed an AR interface. Users had plenty of suggestions for improvement. And in a follow-up work, I started to actually see the rewards by developing an interface that could actually explain suitably for users the shared control. And some of the key visualizations I found that were helpful were this rear view display, which is able to show the reverse motion of the wheelchair, much like sort of what you would find in modern cars. The other one was a mini map panel. This is similar to what you might find in aircrafts, and it provides a driver localization information. And then last but not least is this idea of having red spheres overlaid on points where collisions were detected. And this was rated extremely highly by all users. And it's important to note that as most headsets, augmented reality headsets, because virtual reality doesn't have this problem, you're fully immersed, but augmented reality headsets are notoriously known for having poor fields of view. They're improving, but they're still not quite there yet many times, especially not the HoloLens. An important feature of these spheres was this directional arrow that would signal the location of collisions when these spheres were not in the field of view of the user. So the overall visualizations ended up being far more effective, and importantly, bringing it back to this idea of model misalignment, it demonstrated that users were able to better overcome typical events that show misaligned models, such as doorways or getting stuck in place. Okay, after my PhD, I transitioned into exploring virtual reality and other ways of exposing the inner workings of a robot's autonomy. And I started to look at more complex settings than planar robot navigation, like in the wheelchair case. And robot arms are a great place to start because they're challenging for most novice operators to control. Due to the fact they have high degrees of freedom and unintuitive dynamics. The other important thing to note here is that this particular experiment setting I looked at tried to have a robot arm teleoperated in virtual reality to screw in a wooden bolt. So these wooden bolts you can see attached to the box on the right. And this required high precision. So this was another reason why it was a great complex task for telemanipulation. In terms of how I implemented the shared control, this is actually work with my collaborator, Philip Long. I'm not going to dig too deep into the technical details of it, but there were these geometrical constructs known as polytopes, which enabled the shared control version of this this system to generate collision-free motion during arbitration. So inspired, as I continue on this line of the importance of getting user-informed feedback when thinking about making explainable cues on a robot state, inspired from my research on robotic wheelchairs, I actually ran a pilot study before the final experiment, where I asked users to select from these 4 virtual reality interfaces on the left-hand side. And in 1 and 2, all the users could see were the images from a camera attached to the robot arm. And there were 2 different types of visual cues. But in 3 and 4, the user is actually able to see a third-person perspective of the model of the entire robot and environment. And this is harder to generate in practice, especially when you think about unconstrained environments. But it is usually a way more effective interface option. And then in terms of the differences between 1 and 2 and 3 and 4, the 2 visual cues that are available were either the geometric polytope on the left-hand column or this more simple compass illustrating the direction that the user should move towards when trying to screw in a bolt. So from this pilot study, we ended up converging on the model configuration that you see on the right-hand side. The simpler compass guide was preferred by most people. And the other important thing that was found was that the end effector camera really needed to be moved a lot closer to the actual end effector. So these final adjustments, like moving the camera closer to the end of the arm, they were critical observations made by users, not us as designers. So to evaluate the system and to give everyone a better sense of what the task looked like in a video, we asked participants to teleoperate the arm with and without shared control. And our results showed partially promising findings in favor of using the visualizations to explain the underlying shared control, specifically in terms of improving task safety. But I do want to emphasize that extended reality for robot to human transparency is still a very open research direction. And so there's still many ways to improve the types of user interfaces that are suitable for these applications. So I'm not going to stray away from my research on visualizing a robot's internal states and look at other areas of relevance when using extended reality headsets to enhance human-robot collaboration. And I'm going to start with the inverse notion of human-to-robot transparency. So far, the focus has been in this talk on humans understanding a robot's behavior and their underlying reasoning. But what about the other perspective of robots understanding a human's reasoning or their latent states? Now, in my past work, I've investigated this user modeling problem in the context of, say, human intention estimation, such as understanding where does the wheelchair user want to go, as well as in the context of ergonomic posture analysis. So deciding how the robot should hand over a heavy object to a human receiver. Now, there are many different problems you can explore in this area of human behavior modeling. But what I really want to highlight is that extended reality headsets are especially useful in addressing this problem, specifically because they have multimodal sensory information all contained into this one device. So you can capture visual data, spatial input data on hands, eye gaze, head pose, sort of localization information, very powerful sensor, really. And you can then apply it to problems like egocentric action recognition. So with access to this information, you have a lot of things you can do in terms of user modeling, but you will have the additional problem of just degradation in, say, signal quality. So because it's an egocentric perspective, there might be a lot of motion blur. It's also hard to annotate data. There's a lack of existing data if you're using machine learning approaches. But these are all hurdles that we as a community will gradually overcome. So I do encourage people to also think of the headset as a sensor rather than just a feedback tool. And in line with that direction, I also want to mention great for not just modeling the user, but also the environment itself. So many augmented reality headsets already possess state-of-the-art algorithms for localization and mapping. And these can be really useful, like in this right-hand visual of a task that we did in my lab. We're here grounding information about where the objects, these cooking objects are, relative to a user making coffee. And so the same idea can be extremely useful if you translate it to, in say, informing a robot about its mapped environment. Now, while user and environment modeling are key features of extended reality headsets, and I think they have huge potential for collaboration, the way that I want to end this talk is on the importance of the user interactability. So take this video of a robot capable of acting on objects in its environment. By exposing the affordances to a human wearing the headset, and by allowing the wearer to actually select different behaviors, like give me the teddy bear or clean up the teddy bear, the user is then not only able to understand what the robot is doing, but also able to actually explore the robot's capabilities. And so this, in my view, falls into the broader idea of programmable or editable robots. And this is a growing area of interest in extended reality for robotics. These two examples here are from pretty recent works that were well acclaimed. On the left-hand side, you can see people are able to actually adjust, say, the motion constraints of a robot in real time. And then on the right-hand side, people are teleoperating a robot using its digital twin model. So you can either drag and drop, say, the end effector to control where it moves its arm in a sort of kinesthetic programming sense, or you can actually embody the robot and teleoperate its end effectors. And I believe this programmability through extended reality is going to help make robots more explainable, because users are going to be capable of actually exploring the robot's behaviors, not just looking at their visual state and how they work, but actually modifying what they do and editing them. And to bring this back to my research on teleoperation, so recall that I said at the beginning of this talk, or earlier in this talk, that robot arm teleoperation is generally a complex task, so not easy for most users, or at least beginner users. Share control is a way of introducing autonomy to assist the operator, but it traditionally also gives rise to confusion, ignores the unique preferences and capabilities of different users, and it's also not always great at adapting or evolving to task changes. So in a very recent work, my colleagues and I tackled these challenges by proposing a user customization framework. And this allowed users to actually edit the arbitration behavior of the share control through a feedback interface. We specifically looked at a virtual reality headset as a feedback interface. And we formalized this framework in the hopes of boosting teleoperation proficiency, but also improving operator skills and how they learn to use the share control robot. And we explored this particular framework that we proposed in a BuzzWire game setting. And the reason we chose this setting is because it's a well-known setting for people when it comes to dexterity training. So people do it quite often in like surgery training or motor skill rehabilitation. And it's also then a great testbed for teleoperating, say, a robot arm due to the precision required. And to actually explore the sort of capabilities of different approaches in our framework, we conducted a between subject study with users, 12 users, comparing 3 different teleoperation modes across 4 sessions per subject. And this lasted about 2 weeks as we alternated between sessions, we alternated days. And the key thing to note is that we wanted to evaluate the generalizability of how well users understood the underlying share control. So each subject completed the game with a different test bed in the last session. This test bed that you can see in the bottom right, which has the thicker wire and the higher curvature at the beginning and at the end. So here's just a video illustration of what the task looked like. The first subject group simply performed the task using direct teleoperation. So there was no share control. Here you can see the different perspectives, such as the remote operator in the top left, the physical robot performing the game in the top right, and the virtual replica in the bottom left. There's also some feedback there. You can see that red lights go off when there are collisions. There was also haptic vibrations in the controller. And then the second group was this performance-based share control, where feedback was provided on how the robot share control worked and what the arbitration looked like, but they were not able to actually edit these parameters. And then finally, our proposed user customization method. That's where participants were presented with the same spider chart as in the previous group, but they were also able to actually edit the parameters according to their preferences. And this was the one that we found had the most sort of interesting findings, as I'll show you now. So first, as one might expect in the baseline session, which was the one where everyone was just trying out the robot for the first time, we found that the performance-based share control method had the safest performance, but the slowest times. However, the direct teleoperation had the fastest completion times. And this is something that's typically found in the sort of literature on teleoperation. But what was then interesting is that the user customization group started to have far better improvements in performance across sessions, with, in fact, the least number of collisions and fastest times when it came to the transfer, the final session. So these results generally hinted in favor of a more generalizable skill set for users when they were able to customize the robot's behavior. And we also found that the arbitration parameters that were defined according to user performance, they converged to a conservative setting, specifically prioritizing safety. What was interesting about the user customization parameters on the left-hand side of this spider chart is that they demonstrated greater variety in what users chose. And I'm not going to dig into the specifics of these different arbitration parameters, but you can consider them as factors relevant to the specific buzzwire task, as well as the general idea of like skill in robot teleoperation, such as don't crash into obstacles. Okay, just to wrap up, because I'm conscious of time, I have shown all my research up to date, at least on extended reality and human-robot collaboration. I want to highlight one last area of research that's worth discussing, which is extended reality for learning from demonstration. I think it's got a lot of potential. I think it could provide real-time guidance to users on whether their recorded demonstrations are actually useful for a robot to imitate or not. I also think that the immersive experience of, say, embodying a robot as you take over its motion could be far more intuitive than using like a handheld controller. So here you have like a hand that's actually, a person has their hand kind of mapped or retargeted to the manipulator of the robot arm, and then they can actually control it just as they would their hand, which gives them possibly a more intuitive way of guiding the manipulator. And then finally, I also think that extended reality may make demonstrations be collectible without physical hardware, so without an actual robot necessary, just a digital twin. And this could be a far more cost-effective solution. So that concludes my talk. Let me reiterate that I mostly covered the topic of the robot to human perspective on this problem, but I generally believe effective human-robot collaboration requires explainable interactions. And I think bidirectional communication of an agent's intentions is vital here. So extended reality headsets are just one medium of communication that I found especially promising in improving a user's mental model of the robot's behavior. But I also believe these headsets have the ability to improve a robot's awareness of the internal user states. And I think there are many interesting open research questions to continue exploring, like how do we actually define and evaluate model misalignment between a user and robot? Or what is the best sensor feedback for communication? Is it the visual audio channel? Is it a combination of many modalities? And then finally, the direction I'm most fascinated by is the idea of studying the interplay between how the internal models of humans and robots adapt over the course of a task. So if a robot's model of a user is updated online, and the user can actually visualize these updates, will the user and robot co-adapt, or will a conflict begin to arise? And I think resolving the potential for conflict by better understanding this mutual model adaptation process is going to be crucial in terms of long-term human-robot collaboration. Anyway, that's it for my talk. Thank you for your attention.
Thank you very much, Mark. It's a very, very interesting presentation and topic. It's moving very fast, actually. From if you compare the models and the technology that was more than 50 years ago to how it's evolving nowadays, it's really catching up a really nice momentum. So it's nice to have to have people and to know more about this kind of technologies. Okay, so now we proceed to the set of basically to the stage where questions are asked from the audience. So does anyone have a question?
Albert, yeah, it's Diego.
Sure.
Mark, as you know, from the last time we talked in the presentation that you had with Philip, we're doing research in our research group with somewhere in the collaborative intelligence for safety critical application research projects that will benefit very much from some of your findings. So, Ayush was working on teaching by demonstration, and one element for us is what feedback can be given to the operator. So what you were suggesting here as using the extended reality would not only solve the problem, but also in terms of the European upcoming regulation on safety of machinery that requires this feedback to be given for any human robotic interaction. It would also solve that problem because effectively the digital twin can show to the operator how good or bad the demonstration is before it's pressed on, as yes, go with that, because especially given but how do you find a non-expert user interfacing with the extended reality? Because the other aspect of it is that it is often overwhelming in terms of the amount of information and the different type of views that that has to be managed.
Yeah, definitely. I think that's a great question. I don't think this is going to be a one-off solution is my answer. We design an interface and it works right off the box. I think the way that we integrate robots into manufacturing sites nowadays always assumes that there's going to be some kind of training of operators beforehand. For me, I'm starting to think more about how we can actually ease the training of users as opposed to making the, best one user interface solution for all. So I think it's more to do with actually accepting that you won't come up with the best solution right off the mark, and instead look at how we can actually create intuitive ways of training users to become accustomed to these interfaces and the different problems of using these headsets.
Thank you. And I might leave then the floor to other people asking questions, but one of the reasons also I invited you was also related to another project about telerobotic where, and I'll probably organize a meeting with the other researcher, Ines. She's been looking at how interface affects performance in telerobotic, which is very, very similar to the dexterity task that you showed. For her also was about, but also how to display that information. We found a complete lack or gap if you like, in the literature and in the guidelines, in the standard, on what type of interface should someone have when operating an haptic device for any type of remote operation. And she found, but are only preliminary finding, that of course alignment between the virtual model and the 3D camera view, or the camera view that you use for providing feedback to the operator, seems to be the one that works best. Any particular findings or highlight from your perspective? Because the piece about the customization was particularly relevant for this. Instead of going for one guidelines, flexibility to let people adjust their own could still be potentially a winner. I don't know what your thoughts are on this.
Yeah, so I think that allowing, one of the key perks of having a visual interface and not just say a haptic channel is you can actually interact, that's that user interface to say how the robot behaves. And so not just in terms of like how the robot functions in terms of its movement and control, but also just how you want to interact with it, how you want to send actions for it to perform. And so I think that the key thing here is, much like we all have different ways that different mouse sensitivity preferences, different smartphone customization features, I think we need to expose that type of information to how we expect people to use robots. And probably there'll be a combination of modalities to think of. So it might be that a person doesn't necessarily want to use an extended reality headset. They might go for the monitor and the haptic channel, or just the monitor display. But in all cases, you need to allow them the ability to sort of select those modalities and also customize within modalities, say how you want to send actions to a robot.
Thank you, Mark. Quite clear. We definitely need to follow up with you as advisor on the others.
Yeah, that'd be great. Thank you.
Can I just ask a question following up Chiara's question? Because in that experiment as well, they have found challenging the teleoperation of the cobots, because basically, and I've seen also in some other areas, for example, in nuclear as well, the robot that is being controlled remotely has to be connected to the same network, and kind of it's telerobotic, but it's also kind of local. So everything has to be, local. How far are we from actually, doing telerobotic controlling, but from outside local networks?
See, that's an area that I don't think I have enough expertise in. I have done some works where we're going outside of local networks. In fact, you end up needing a full communication team to sort of accommodate this. I have been in touch with networking people who said that the state of the art capabilities of like 6G and latest next G technologies is going to be able to support the sort of fidelity you'd need and the kind of reliable communication you'd need. So this is definitely an area of research I've briefly encountered in even areas like share control, like how to kind of have the autonomy kick in when you have a loss of communication between the arm and the operator. But in all cases, it's not something I have expertise in. I think it's necessary to have a team of experts on and people addressing, but definitely not my area of expertise.
Okay, no problem. But thanks a lot. I really appreciate your insights. Okay, so is there any other questions from the audience?
Hi, hello, Philip here. Can you hear me?
Yes,
Yeah,
we can.
Mark, thank you very much for the presentation. I actually have a question in relation to the type of feedback provided between the human and robot agents. And the different setup you provided in your research. So the teleoperations assume that there is a disconnect, that there's a remote operations between both agents, and when they both are collocated in the same location.
So is your question about like how the disconnect occurs, or?
No, it's about the observable difference between the feedback provided to human operator, considering those two different setups.
So the two different setups is in between the works I presented, or?
Yeah, so you use mixed reality or virtual reality. It depends if it's the telerobotic or more collocated. Based on your research, was there any difference between these two setups in the way how you provided the feedback?
Yeah, definitely. I think that the feedback one is considering, like in my case, I looked at when you've got co-localization, you start to think about features that are kind of more grounded to the environment, and you know that there's this third person perspective of, say, the user interacting with the robot, and that could change things. But there's also the idea of the robotic wheelchair where you embody the robot itself. And that's more similar to, in fact, teleoperation, like in virtual reality. So your interface design is certainly going to change depending on whether the person has that third person view or not. And in fact, in the virtual reality teleoperation, that's kind of what I alluded to when I said you want to have the whole view of the robot and the environment. And while that might not be achievable in a real world setting, it's definitely desirable because it improves or at least makes it easier to expose information to the operator in a kind of informative way. I hate to do this, but I think I only have time for like one more quick question because I actually have to hop off now.
Mark, thank you very much.
So, yeah, I hope that answered it. Sorry, Philip.
No, I think
Yeah,
we're going to close with this question. We're going to close this session. Mark, thank you very much for your time and for this very insightful presentation, and looking forward to hearing more from you in the future.
Perfect. Thank you so much.
Take care, and thank you everyone for attending.
Bye.
Thank you. Bye-bye.
Thank you, guys. Diego, see you later. Talk to you later. Bye-bye.